Hey there. I don't have any clean ISU stuff, so I've got a black and orange training shirt. So this is my best for Bengal Wednesday. Hope you're all having fun out there in an appropriate socially distanced manner. So today we're going to do a quick review on exponential and logarithm. Those are things that you've studied before, and they are by far the most useful tools in doing applications, and so it's important to keep them fresh in mind. So that's what we're going to do: put them fresh in mind. These come up in three ways, and so one is the half-life, and one is the rate, and that's a periodic rate, and one is continuous rate. And so these all have their uses. The situation is this: half-life. Half-life is a time, and that's what's in the handbooks. And so it's important to be able to work with it, because when you're reading about things that are subject to exponential models, you'll be reading about the half-life, and then you have to go into the other stuff to see what's going on. So the half-life is a time, and it's in the handbooks, so you'll definitely run into it when you're doing any kind of application. And just call me crazy, I'm going to call it H. The periodic rate is something like annual interest or daily rate of growth or something like that. So it's periodic. It's a rate, so it's bacteria per hour, something like that. I'm sorry. This is 2020. We don't do bacteria per hour anymore. We do viruses per hour. And in honor of them, I'll call that rate V. And the last thing we see is the continuous rate, which is the theoretical construct. And that's what we use the most in calculus. It is the cleanest thing for doing calculus. And so what you need to be able to do is read in the handbook, do some lab observations, come to a continuous result, do some calculus, and then go verify that that's what happened in the lab, or go into the handbook. So going back and forth between these is a standard part of working with anything that has an exponential model. So these are easier than people make them out, and so and so I'm going to write down what the exponential function is. I'm not going to include the initial amount. You remember, all of these have the amount at time 0 as an initial amount, and so I'm going to skip that. And what we have instead for the half-life, it's just a matter of rearranging the data on the page. If you've got the half-life as h, the function is 1/2 to a power. The power is a fraction, and the fraction is t, that's the variable I'm assuming, over h. All you do is put h in the right slot, and you got the function. Good. In the virus per hour kind of thing, what you have is you've got a certain amount, and then you add that every hour. So an hour later, you would have a function that looks like this. You got to be careful. T is the variable here, and V is a constant that you might observe in the lab or something like that. So this is the periodic rate. One potential gotcha with periodic rates is if you change time units. If you start with years, so if you have an interest rate of 4% per year, that's something that happens a lot in financial applications. Well, that means that the rate, I'll still call it V, is 0.04. That's just converting the percent to a decimal. And then, but if you do it monthly, well, if you only leave the money in the account for 1/12 of the time, you only get 1/12 of the money. So that then now the rate becomes a fraction, 0.04 over 12. And for pity's sake, do not simplify this. Put this in your calculator just like this. Let the calculator do the work. The other problem is you've got 12t payments per year, if you've done things monthly. And again, for pity's sake, don't put that in, well, put that in your calculator. Don't try to simplify it. Okay. The last one is the simplest form, and that's just e to the RT. So there's e is the exponential base, the base of natural logarithms. You're very quickly going to find out why natural logarithms are natural, and so, but there it is. So here are the three forms. There's a thing on Moodle called 3 cups of e that goes through going between these, and that's the way you'll see it. So if you read it out of a handbook, you use this form of the function. If you measure it in a lab, you use this form of the function. If you're doing something more theoretical, you use this form of the function. Okay. There's one little gotcha here also. It's not a gotcha, it's a big tool. It's the logarithm. Logarithm is a term that has confused people for, it's coming up on 400 years. And someone who had too much Greek and Latin for their own good came up with the term logarithm. The term really should be exponent. So let me just remind you of this basic thing about logarithm. It's one of the basic properties is if you take logarithm of x to the y, it doesn't really matter what x is or y is. X has to be positive, but if that's the same thing as y times the logarithm of x. And that's the key computational algebra tool to go between these three kinds of functions is take logs, get the exponents where you can deal with them, and go with that. So there's a little thing. All of the great leaders in history have, when confronted with exponentials and having to solve for something that's in the exponent, they say, take the log of both sides. That's what Abraham said. That's what Jesus said. That's what Buddha said. That's what Allah said. The only exception is Yoda, who did not say take the log of both sides. Yoda said, the log of both sides take, so do that.